Assalamualaikum, students. We have studied in this whole course about vector analysis and how we can differentiate vector, how we can add vector, how we can integrate the vectors and types of it, and then we have studied about transfer coordinates and transformation of coordinates, types of coordinates. In the same way, we have studied about tensors and what are tensors, how we can derive the relation for the tensors. Now we'll study some further properties relating to complex number. We have studied some properties about complex number, that what are complex number, how we can add, subtract, and apply different rules on complex number. Now we'll study further some theorems or rules about complex numbers. The complex number, the term which we'll use here, the equation which we will have to derive according to the complex number is known as Cauchy-Riemann equation, which is also known as CR equation. We'll introduce it and then find its analytical function, derive the Cauchy-Riemann equation, and the examples related to this. We'll start that what is Cauchy-Riemann equation. Necessary condition for a complex function. Therefore, f of z, if we say that f of z is a function of u which depends on x and y, plus iota v which is a function of x and y, to be analytic in a domain D, is that in the domain D u x y and v x y satisfy Cauchy-Riemann equation. So we say that if we have a function which is equal to u and v iota v, and if we say that this is an analytical function, so we can say that u and v in any domain, so we can say that u and v satisfies the Cauchy-Riemann equation. So we'll describe that what is Cauchy-Riemann equation. The statement of Cauchy-Riemann equation is this, that curly u over curly x is equal to curly v over curly y, and curly u over curly y is equal to minus curly v over curly x. It means that if you derived one term, the other term is opposite to that. It means that curly u over curly x and curly u over curly y, the same way curly v over curly y minus curly v over curly y. Cauchy-Riemann equation is the equation which gives a relationship between the derivative of real and imaginary part of complex function. It means that Cauchy-Riemann equation is that function which gives the derivative relationship between derivatives of real and imaginary part of complex functions. Now, what is its analytical function? A complex function is said to be analytic on a region if it is complex function differentiable on every point. The term holomorphic function, differentiable function, and complex differentiable function are sometimes used interchangeably with analytical function. So it means that analytical function is that function in which the complex function is differentiable at any point in the region, and the term for holomorphic function, differentiable function, and complex differentiable function is also used for analytical function. To find the analyticity of a complex function, we have a set of two equations. If these equations are satisfied, then the function would be analytic or differentiable. So what are the two equations? What are the terms? We can say that this function is analytic or differentiable. Now the introduction about the Cauchy-Riemann equation. Consider that we are going to derive the relation for Cauchy-Riemann equation. How we can derive this equation? Consider the complex function omega is equal to function of z in the domain D, and we can say that omega is equal to f of z, which is equal to u of x y plus iota v x of y, where we have studied earlier that we can write z is equal to x plus iota y, whereas here u and v are the a function of x and y, so that's why we are using here the terms u and v, where u is the real part of the complex function and v is the imaginary part of the complex function. Now to check whether the complex function is differentiable or analytic, we can say that the equation must satisfy the situation that curly u over curly x must be equal to curly v over curly y, and curly u over curly y must be equal to minus curly v over curly x. These equations should be satisfied. So now we'll start and drive this relation as let now omega is equal to f of z is equal to f of x plus iota y. Also we can say that omega is equal to u x of y plus iota v x of y, and if z changes by del z, then we can get f z plus del z is equal to f of x plus del z plus iota y plus del y. Now rearranging this whole equation as f of z del z is equal to u x plus del y and y plus del y plus iota v x plus del x plus y plus del y. So we have substituted simply we have just substituted these values according to the situation in the given formula of f of z, which is equal to u and v. Now by definition of derivative, we have that f prime of z can be written as equal to limit del z approaches to 0 f of z plus del z minus f of z over del z, where del z is equal to del x plus iota del y, and del z approaches to 0. So we can say that del x approaches to 0 and del y approaches to 0. So we can have this whole simplified equation as f prime of z is equal to limit del x approaches to 0 del y approaches to 0 u of x plus del x y plus del y plus iota v x plus del x y plus del y minus u x of y minus iota v x and y over del x plus iota del y, where we know that if z approaches to 0, then x approaches to x naught and y approaches to y naught. Now we first moving along the real axis of x is changing and imaginary axis y being constant. It means that we are just considering the real part and ignoring the imaginary part. So the equation will become as del z approaches to 0, del x approaches to 0, and whereas del y is equal to 0. We have substituted del y equal to 0 in the equation where del y is available. Applying an above equation, we got f prime of z naught is equal to limit del x approaches to 0 u x naught plus del x and y naught plus iota v x naught plus del x y naught minus u x naught y naught minus iota v x naught y naught dividing by del x. Now separating the real and imaginary part, the equation will become as limit del x approaches to 0 u x naught plus x del x y minus u x naught y naught del x plus iota limit del x approaches to 0 v x naught plus del x naught y naught minus v x naught over del x. It can be seen that these are the derivatives of u. It can see that these are the derivatives of u with respect to x first term and v with respect to y second term. So we can write this whole equation as here y naught is also written with it to get the proper, and this is not y, this is also y naught. So we'll get this equation, and we can see from this equation that this is the derivative of u with respect to x, and this is the derivative of v with respect to x. So the equation will become as f prime of z is equal to curly u over curly x plus iota curly v over curly x. Now moving along the y-axis, or you can say imaginary axis, so we can say that z approaches to z naught, and we have y approaches to y naught, and x is equal to x naught, which is equal to constant. So we can say that, and also we know that del z is equal to del x plus del iota y, as we can see that del x is equal to 0 and del z is equal to iota del y. So we have substituted these values in this equation. We get that f prime of z naught is equal to limit del y approaches to 0 u x naught y naught plus del y plus iota v x naught y naught plus del y minus u x naught y naught minus iota v x naught y naught. when we have substituted the values according to the situation. So we'll get this equation. Now after rearranging this equation or separating the u and v terms, we'll get u x naught y naught plus del y minus u x naught y naught iota del y. In the same way, limit del y plus limit del y which is 0 iota v x naught y naught plus del y minus v x naught over iota del y. Now we will get as f prime of z is equal to 1 over iota curly u over curly y plus curly v over curly y. If derivative doesn't exist, then special derivative. So if the derivative does exist, then special limit of the function must be equal. Now equating the equations as equation number 3 and 4, we get curly u over curly x is equal to curly v over curly y, curly u over curly y minus curly v over curly x. So how we have equate this whole equation, or you can say that how we have find this negative sign in this equation. We have got this negative sign like this, that we have multiplied and divided multiplied this whole equation with iota, multiplied and divided this whole equation with or you can say that I have substituted multiplied this first factor with iota. Sorry, we have multiplied this whole equation with 1 by iota. So it will become iota square which is equal to minus 1. So that's why this whole equation will become equal to as minus curly v over curly y plus curly v over curly y. So that's why this whole equation is equated as, when we keep those two equations equal, we'll get curly over curly x is equal to curly v over curly y, and curly u over curly y is equal to minus curly v over curly x. This minus sign is introduced from this equation. Hence, this statement is proved that what is Cauchy stigma equation. How we can say that the real and imaginary derivative of real and imaginary part are equal. They have a relationship between them. The question here is given as f of z is equal to z square is equal to x square minus y square plus iota 2xy. Is this differentiable everywhere? And then f prime of z is equal to 2z. If we find the relation according to the situation. To verify this Cauchy-Riemann equation are satisfied as u x of y is equal to x square y square, because we have separated its variable, and u v x of y is equal to 2xy, and the real part according to this situation, the real and imaginary part is this and imaginary part is this. We have separated its term, and to find that if we want to differentiate this whole equation with respect to x, u of x is equal to, we'll get as curly u over curly x will get as 2x. In the same way, if we differentiate it as curly v over curly y, curly v over curly y will get as 2x. So we'll get the same answer. It means the first state the condition is satisfied. In the same way, when we differentiate this equation curly u over curly y, we get as minus 2y. In the same way, when we differentiate it as, we'll get if we differentiate with respect to as curly u v over curly x, will get 2y. So the situation is similar. So we get a result similar, and the situation of the Cauchy-Riemann equation is satisfied. Moreover, we can say that f prime of z is equal to 2x plus iota 2y is equal to 2x plus iota y, when we have substituted these values as 2x plus iota 2y, 2x plus iota y is equal to 2z, to get the value of z, which is verified from here as well, that if we differentiate this whole equation f prime of z with respect to x, so we'll get this situation here. Since the Cauchy-Riemann equation necessary condition for the existence of derivative of function f at point z naught, that can be often used to locate points at which f does not have the derivative. Example number 2 is that if f of z is equal to z square, we have u of x is equal to x square plus y square and v of xy is equal to 0. If the Cauchy-Riemann equation are to hold at point xy, it follows that 2x is equal to 0 and 2y is equal to 0. Why? Because we differentiate u with respect to x and v with respect to y, we get 0, and here we get 2x. And why we differentiate u with respect to y, we get 2y, and differentiate with respect to y, the other part will get 0. So 2y is equal to 0. So we can say that x is equal to y is equal to 0. Consequently, f prime of z does not exist at any non-zero point. This is the assignment that solves that example according to Cauchy-Riemann equation, that f of z is equal to cos 2z and f of z is equal to sin 2z. In the same way, u is equal to 2x minus 2xy, find v, and u is equal to this, find v. I told you its part as we have the equation as curly u over curly x is equal to curly v over curly y. So it means that firstly we'll have to differentiate this whole equation with respect to x. We'll get as 2, derivative of 2x is 2, minus, and derivative of 2xy is minus 2y, and the equation is equal to curly v over curly y, because we have to find the value of v. So how we can find? We have to take this curly y here, so it will become as curly v is equal to 2 minus 2y d curly y. Now integrating this whole equation, we'll get as d is equal to, integrating this as with respect to y, we'll get 2y minus, and we'll get here minus 2y square by 2, whereas this 2 is cancelled, plus c. So this is the value of v. In the same way, you'll have to solve this question number 4. And question number 1 and question 2 is solved in this way, that we have cos of 2z. You'll have to find its derivative. First you'll have to split the z and then find its derivative with respect to the situation to find the possible solution according to the given condition. Thank you. Thank you.